Let's now exploit some of the information we've learned about bifurcations to understand the phenomenon of catastrophes. So a catastrophe in the context of a one-dimensional nonlinear dynamical system is a change in the stability of fixed points as control parameters vary. And our generic example here is the following equation: x dot is equal to rx minus x cubed plus h. So let's define this thing to be f of x. Are positive, and so our control parameter is h, and basically what h is doing is controlling the height of the function in the x dot plane. And as we'll see, as we change the height of the function, the number of fixed points changes, and the types of phenomenology that occurs changes as h changes. So to understand what's going on, let's plot as a function of x dot. So let's first consider the case where x is fairly large, so that our function, which is a cubic equation that is positive for x negative and negative for very positive x, and has an inflection point. So let's imagine that h is larger than a critical value hc that I'll define in just a moment. And so the function looks something like this. So this is for h larger than hc. And here we see that there's a single stable fixed point at some positive value x. So there's one fixed point. Now let's lower h to hc, and the way it's defined is the following, is that hc is defined in such a way that the function just kisses the x-axis, where the left minimum first kisses the x-axis. And so this is h equals hc. And here we see that there are two fixed points. And there's a fixed point of positive x, which is stable, and a fixed point at a negative value of x, which is of this marginal point, which is unstable coming from the right and stable coming from the left. Then if we go to a still smaller value of x, our function looks something like this. And I've engineered it so that this is the point at which the function is actually equal to 0 at x equals 0. So this corresponds to h equals 0. And here we have a stable fixed point at a positive value of x, a stable fixed point at a negative value of x, and an unstable fixed point at the origin. So we have three fixed points. And in general, when h is between plus hc and minus hc, there will always be three fixed points. If we then decrease x still further, just kiss on the positive axis. So this is for h equals to minus hc. And here again we have two fixed points. And this is a stable fixed point at a negative value of x, and then the marginal point, which is stable on the right-hand side and unstable on the left-hand side. And finally, if we decrease h below minus hc, then our function only crosses the x-axis in one place over here. So there is h less than minus hc, and there's just one fixed point. The critical value hc is determined by the point at which f of x is equal to 0. So we need to find the point where f of x, f prime of x, is equal to 0. And it's a simple exercise that I'll leave for you to do. F prime of x is equal to 0 at x, and let's call this xc, the critical value where the first derivative of the function is equal to 0, at plus or minus the square root of r over 3. And then the value of f of xc, so if we plug in xc into the equation for f of x, it turns out that f of xc is equal to plus or minus 2 r over 3 to the power 3 halves plus h. So when this point of zero slope kisses the x-axis, that means that the value of f at xc is equal to 0. And so we have to set this thing equal to 0, and from this we infer that hc is equal to plus or minus 2 r over 3 to the power 3 halves. These two critical values of h determine whether I'm going to have one fixed point, two fixed points, or three fixed points. And this is the catastrophe phenomenon that I was describing.